Hello and welcome to another lecture of classical motion of a single particle. So, we have already introduced the concept of stability and how that is associated with respect to the phase space trajectories very close to the fixed points. So, the concept is basically that if in your dynamical system you just give a very slight perturbation in the phase space in terms of the phase space coordinates, okay, with respect to the fixed point or with respect to one of the fixed points. Okay. If those perturbations are getting aggravated or getting more and more important or getting strength in time, then the fixed point is called a non-stable or unstable fixed point. Okay. On the other hand, if you give a slight perturbation with respect to a fixed point and you see that that perturbation gets somehow diminished or reduced in time or does not increase in time. Okay. In both cases you can think of a stable fixed point. So, for a two dimensional phase space flow we simply continue our discussion. We said that if you have a set of equations of the evolution, okay, where the phase space coordinates are x and y. So, the equations of evolution they are given by simply x dot is equal to some f of x and y dot equal to g of x and y. Then we said that to determine whether the fixed point x star y star is a stable or unstable fixed point, we have to slightly perturb those values. So, from this we have to give some small epsilon and with respect to y star we have to give some small delta, and then we will check that how these equations would behave, okay, in the neighborhood of this fixed point. And then we said that we actually can find that this x dot and y dot in the neighborhood of this fixed point can be written as a matrix which is given by del f del x del f del y and then del g del x and del g del y, all evaluated at the fixed point, concerned fixed point, okay, times the a vector which is constituted by the phase space coordinates will be exactly equal to the phase space velocity vector, that I called phase space velocity vector. So, phase space velocity vector. I can call this one as phase space position vector. Okay. Now, we said that for this matrix of course, it will have two eigenvalues lambda 1 and lambda 2, and if these eigenvalues of course can be real or complex. Since they are constituted by real entries, the complex eigenvalues will always be in conjugate. Now, if they have a real part, okay, and an imaginary part, and this real part is positive, and here for the two eigenvalues, if at least one complex eigenvalue has a positive real part, and for the real values if any one of those two has a positive real value, okay, then we will be led into a case of unstable fixed points, okay, plus positive. Okay. But at least, so I am just making this highlighted, at least one of lambda 1 and lambda 2. Okay. On the other hand, for a stable fixed point, both of them should be, I mean should be of a nature where the where they are negative, okay. And here for the complex root the real part for both of them should be negative, okay. If at least one gets positive, then we have unstable fixed point. Then also there is a specific case where this real part is 0 for the complex roots and the imaginary part is the only surviving part. And of course, in that case you can say that, okay, although there is no decrease of perturbation, but also there is no increase in perturbation, because imaginary part means it will simply always maintain the same magnitude, okay. So, for example, let us say I can always write this lambda 1 lambda 2 like some a e to the power plus I theta, okay. So, since I am saying here for our case this will be, so and this you know that it will be a cos theta plus I a sin theta. So, here for our case this part should be 0, okay. So, actually this thing you can always write like plus minus I beta, where beta is a constant, real constant. And you see that although this will not decrease the perturbation, it will neither increase the perturbation, it will always give. So, basically, so you will find that the perturbation will always have a constant magnitude, okay. Now, and in that case we will find something what we called also a periodic orbit. So, here for this case we find an orbit, okay, which is also stable fixed point usually, okay. Now, in this lecture what I will do, I will actually take one by one several examples where you can see different type of fixed points. Now, before starting that, let me give you a disclaimer, that is many of those examples will not be relevant for classical mechanics. Although this is a course of classical mechanics or classical motion of a single particle, this technique is a technique which you can use in a broad range of domains, and the training is for that purpose specially, okay, at this point. Now, we will actually see under which condition you can actually recover the system of classical mechanics, okay. So, the first example I can start with a very simple example, that x dot is equal to x and y dot equal to simply y, okay. So, I have two state variables x and y and I have two equations of evolution x dot and y dot, okay. Now, if you simply understand this equation, you will easily solve this equation immediately. That simply gives you x as a function of t will be equal to some x 0 e to the power t, right. And for y you will also have similarly y of t is equal to some y 0 e to the power t. X 0 and y 0 are the initial values of x and y respectively when t is equal to 0, okay. Now, you see that if I am giving you some constant value here and here, they need not be equal. So, if I simply say, okay, what will be then x by y, that will be x 0 by y 0, that is a constant, let us say alpha, okay. And so, I will have x is equal to alpha y, okay. So, this is the equation of a straight line in the phase space. So, this type of equations will be represented by the straight lines passing through the origin in the xy plane, which is the phase space for this system, okay. Another point is when t is not equal to 0, okay. So, x is never 0 and the similar is also happening for y. If t is 0, these are also non-zero given x 0 and y 0 are non-zero. So, at which point x and y can be 0? if you just start with some non-zero x0 and y0 values. Actually, if you think that for t tending to minus infinity, it will be going to 0. So, it is an impossible case for this type of motion to have 0 displacement in phase space x and y. However, you see, if you see the equations of dynamics, the fixed point is at x is equal to 0 0. So, the fixed point I write is 0 0. At 0 0 actually you have simultaneously x dot equal to 0 and y dot equal to 0. So, what is the conclusion? That the fixed point cannot be attained in a realistic case from any non-zero motion. You see, that means that the fixed point itself creates a discrete or a distinct point which is well separated from the other straight linear phase-phase trajectories in the phase space. Okay. So, if somehow motion starts in such system, you will never achieve a fixed point. Okay. The fixed point is actually isolated, is an isolated point. Now, if I try to draw such type of phase-space trajectories and the fixed point, actually what I can do, I can draw them. And you can see that there is the origin which is the fixed point for us. I denote this with a red cross. That means the motion has no axis at this point. Okay. Now, if you prepare somehow the system at its fixed point, that means you make forcefully x is equal to 0 and y is equal to 0. That means you are actually imposing x 0 is 0 and y 0 is 0. Then if you have this, then even if time is now changing, okay, your x and y will remain 0. So, there is no motion since the system is initially prepared at its fixed point. Now, let us say if I just perturb the system a little bit from x to x prime and y to y prime, okay, then from their initial 0 0 values, okay, then you will always see that the phase space trajectories are looking like this. Although I am drawing them to be curves, sorry for that, but they are actually straight lines. Okay. Okay. And they are going outward for certain. Okay. Because when t is increasing for both x and y, they are increasing. Okay. So, if x and y, let us say both are positive, okay, so that will remain in the first quadrant and both x and y will increase. If x and y, let us say both are negative, then both of them will increase in the negative sense. Okay. So, you see this type of fixed point and the trajectories, fixed phase space trajectories, okay, they are simply saying that as if the fixed point does not like the movement of the particle. Okay. So, whenever some movement is starting in the neighborhood of this particle, of this fixed point in the phase space, the particle is actually, or the state of the particle is actually moved away from the fixed point. So, in a sense it is repelling, okay, the states of motion. This fixed point is repelling, okay, and actually it looks like just like a star who is radiating some light and energy, okay, outward like sun. Okay. So, this type of fixed point is known as a unstable node, okay, and a repeller. Since it is repelling, okay, they are called repeller. Okay. Now, what is a node? Node is a special type of fixed point, okay, for which if you just make a little bit of perturbation, okay, with respect to the fixed point and very close to the fixed point, of course, then the matrix which is formed, okay, it will always have two eigenvalues which are of the same sign. So, here to justify whether this is node or not, we have to find the coefficient matrix, okay, in phase space. So, I am going to this equation once again. Now, this equation can now be written in a different form, that is x dot and y dot, and I can just simply write that is equal to, so here it will be x and y. So, in order to find those two equations, I actually write 1 0 0 1. Well, this is simply the unit matrix, okay, of order 2. So, this is already diagonalized and both of the eigenvalues, they are simply 1 and 1. Okay. So, lambda 1 2, they are simply 1 and 1, okay. But both of them are of the same sign, both of them are positive. So, this is a node, and since you see that the trajectories, phase space trajectories are going away from the fixed point, it is called an unstable node. That means, the perturbation or the disturbance has increased, because this is the amount of disturbance, with time it increases, okay, in this type of thing. Okay. So, this is all about this unstable node or a repeller. Okay. Sometime it is also called stellar type of repeller, okay, because it looks like a star, or you can say unstable stellar node. Okay. Now, one can easily understand that right from this you can intuit what will be the form of the fixed points for this type of system. So, I just write. So, another point is, so I just have to check whether I started by numbering, yes, okay. So, let us say I am now taking this x dot is equal to minus x and y dot is equal to minus y. So, what will be the solution for x and y in this case? They will simply be given by x 0 is equal to x 0 e to the minus t and y is equal to some y 0 e to the minus t. Okay. X 0, y 0, they may be just like the previous case, may be positive or negative, okay, and they may also be equal or unequal. Okay. So, again if you now do, so y by x again is equal to y 0 by x 0, which is a constant. So, again you will have straight lines in the phase space. Straight line with respect to the fixed point, but what is the fixed point? So, right from the beginning you have to understand the fixed point is actually 0 0. So, you see that when you just calculate the trajectories, this is the phase space trajectories, this is not necessarily in the neighborhood of the fixed point. Now, you can do the same type of analysis actually in a different way. You can say, okay, I will actually do a small perturbation, okay, and I can say that this is now, so x dot is equal to minus some x star plus epsilon and y dot is equal to minus y star plus delta, okay, and then you can actually again say that, okay, I now know that will be equal to minus x star plus epsilon and okay, yeah, sorry, the same thing I am writing again, okay, but these two things will simply be then equal to, so this will be epsilon dot and this will be now, so this will be epsilon dot because x star is constant and this will be, okay, delta dot, Okay. So, you can actually instead of writing x and y, you can write explicitly in terms of the perturbations as well. Okay. Now, if you write that, then again you can easily understand that since with respect to the fixed point I am doing this perturbation, the fixed point is 0 0. So, they will be 0 both of them, and finally, you will have the resultant equation to be epsilon dot is equal to minus epsilon and delta dot is equal to minus delta, and so finally, the forms of the equations for the perturbations will be exactly the same for this case, okay, and the same as that of the original phase space coordinates. This was actually similar in this case as well, okay. Although I wrote this for the full phase space coordinates, okay, the same form is true for the perturbations as well with respect to the fixed point, since the fixed point is 0 0. Okay. Now, once I have this, then I can do the eigenvalue analysis, okay, because that is true that in the previous examples I did not do the eigenvalue analysis 100% according to the correct mathematical way. Okay. So, then I can say, okay, I have this epsilon dot and delta dot, and I have my linearized equation where I can see that this is minus 1 0 0 minus 1 epsilon and delta, and that is why finally I actually can have a matrix with lambda 1 and 2 to be equal to minus 1 minus 1. Okay. So, it is a node. So, both of them have the same sign. So, it is a node, and with time, okay, as time increases, these both of them are decreasing in value. Okay. And so, if you now draw actually epsilon and delta, which are the perturbations actually in the phase space, you will find that so I should be mathematically a little bit more careful. So, instead of writing x and y, I can actually write epsilon and delta, which are the perturbation part of x and y, but they are the same because the fixed point is here. Okay. So, I am again write the fixed point with a red cross. Okay. Now, also the fixed point cannot be achieved here by simply this rule for any realistic finite time. This will be 0 when t is now plus infinity. That is also, I mean, okay, theoretically possible, but practically it is not possible. That is why we can say that, okay, it is actually also be an isolated point, this fixed point, but the only point is, okay, also the phase space trajectories will be given by the straight lines, okay, like this, like this, like this, like this, like this. Okay. But now with time, so when x is decreasing, y is also decreasing. So, all of them they are just moving in the inward direction, and that is why this is called, this fixed point is called an attractor. It seems that the fixed point is actually attracting all these phase space trajectories towards itself, although they never meet each other in finite time. Okay. And this is also another case of stellar node, but this node is a stable node. So, stable stellar node. Okay. Now, it is stable, but for t tends to infinity. Okay. So, the perturbation will kill itself at t is equal to infinity. That is why we do not say it is stable, we say it is asymptotically stable stellar node. Okay. Now, we are going to another interesting examples, okay, where you will see that the eigenvalues are not of the same value. Okay. So, I can simply consider this equation x dot equal to x and y dot equal to 2y. Okay. So, what will be now the coefficient matrices matrix? The coefficient matrix will be is equal to A is equal to. So, once again the coefficient matrix is such that I have x dot y dot is equal to A times x y. Okay. So, A will be now is equal to 1 0 0 2. Okay. And if it has two eigenvalues lambda 1 and lambda 2, then of course lambda 1 plus lambda 2 will be the trace of the matrix 3 and lambda 1 lambda 2 will simply be equal to 2, which is the determinant of the matrix. Okay. If you now just solve them, exactly you will find lambda 1 is equal to 1 and lambda 2 is equal to 2. Now, both of the eigenvalues are positive. So, it is a node, as both lambda 1 2 are of same sign. Okay. But they are now not repetitive, they are distinct values. Okay. And now we find the phase space trajectory for the global phase space coordinates, and they will be actually also determined in various ways. One possibility is that you can actually solve for x and solve for y, and then you try to eliminate the parameter, that is the time, okay, and to find the trajectory in x y plane. Or another thing, for this one I can also do, that is just to show you another possibility, that is x dot by y dot, that will be actually equal to dx by dy, okay, and that will be exactly equal to x by 2y. Okay. So, in this problem you will actually have that dy by y is equal to 2 dx by x. Okay. So, finally, by integrating you will have log y is equal to 2 log x plus log of some arbitrary constant c. Okay. So, I can actually again write y is equal to c x square. Okay. You can actually find this in any other method. Now, again, since the what is the fixed point of this set of equations? The fixed point is again fixed point is 0 0, and that is why you will see that whether you are working with x and y or any perturbation with respect to the fixed point, they look the same. Okay. So, I can also draw now a phase space, okay, which is constituted by x and y. And there you will find that the phase space trajectories, they look like this. Okay. And also I am coming to that point, that is also very important to understand. So, they are not actually touching the fixed point, which I can again denote by a red cross over here. Okay. And since you can now solve them, so x dot is equal to x actually is nothing but x is equal to x 0 e to the power t, and y dot equal to 2y is nothing but y is equal to y 0 e to the power 2 t. Okay. So, then actually you can simply say that, okay, although the phase space trajectories are no longer straight lines, okay, both of them are actually, so let us say both of them are actually increasing the amount of perturbation with time, and that is why we can draw this type of thing and with outward arrows. Okay. And unless your t is minus infinity, you cannot reach the fixed point, and that is why this fixed point is still unreachable by this trajectories. Now, this trajectory is actually badly drawn, it should be like this, okay, and it should also be like this. Okay. So, although very close to the fixed point, but can never reach the fixed point. Okay. Such type of thing is simply an unstable node. Okay. The fourth example has very interesting element in it. Till now we are seeing that either the phase space trajectories are going outward the fixed point or going towards the fixed point. So, again you can actually here in this case also you can think that as a repeller. Okay. Now, we will take a specific case where you will not be deciding or you cannot decide whether this is an attractor or repeller. Okay. And for that, if we simply take the case x dot is equal to minus x and y dot is equal to 2y, what we will have? So, of course, the first thing is that the fixed point once again is 0 0. Okay. So, I can just use this whole variables as their perturbations as well with respect to the fixed points, and now you will see that I can have this. So, x dot equal to minus x and y dot equal to 2y simply gives me dy dx, which is nothing but y dot by x dot will be equal to minus 2y by x, and that is why d of log y will be equal to d of log x to the minus 2. Okay. And if you have this plus some constant, of course, and that is why finally the solution comes as y is equal to some constant x to the minus 2. So, x square y is equal to some constant. They are the phase space trajectories, and if you draw them carefully, you will actually see that they look like this. X and y. Okay. So, you will see that you will have trajectories like this. Once again, all of them are very much exaggerated, okay, and they are actually meaningful only in the neighborhood of the fixed point. Okay. I know this is the fixed point, and from this expression actually you can again think that your fixed point can never be attained by just following any phase space trajectory, okay, which is evolving. Okay. So, now you will see that they are actually, they should look like this. So, this type of thing. I am coming why they are like this. So, I am now going to explain why they are like this. First of all, do not confuse them with hyperbola. Okay. So, they are not hyperbola, they are something, some curve x square is equal to 1 over y or some constant by y, or y is equal to c by some x square. Okay. So, now my point is that in first coordinate, okay, so we have to now first solve for this equation. So, we will see if we solve for this equation, then x will be given by equal to some x 0 e to the power minus t, and y will be given like y 0 e to the power minus plus 2t. Okay. So, the first point is that in the first coordinate, okay, when both x and y they are positive. So, simply with increase of time, okay, x is decreasing and y is increasing, and that can only be taken care of if we choose this thing. When in the second coordinate, okay, x is negative and y is positive, that means x 0 is negative and y 0 is positive. Okay. Then what to be done, that when t is actually increasing, okay, x 0 is negative, but it is decreasing with time in negative value, that is why it is going in this direction, and y is still increasing, and that is why it is going in this direction, and that actually justifies this arrow. For the third one, okay, you can see both x and y, they are negative. So, x 0 and y 0 both are negative. Now, t is increasing, x 0 is actually decreasing. Okay. So, it is negative, but it is decreasing in negative value. So, y is increasing in negative value, but x is decreasing in negative value. Okay. So, again you will see that is justifying their arrows. For the fourth quadrant, you can think yourself. Now, by the choice of continuity in the phase space, one can also write on this axis the arrow signs should be like this. Okay. Since they are actually defined very close to the axis, okay, on the axis also they will have a consistent sign for the evolution. Okay. And so, on the axis I take this green color, okay, that will be the direction, okay, of the phase space trajectories. Now, you will see that along y axis it looks like it is a repeller, okay, this one, but along x axis it looks like it is an attractor. Whenever you have this type of position, first of all you will check that what are the eigen values of the coefficient matrix, and here you will see the coefficient matrix is given by -1 0 0 2. So, its eigen values are -1 and 2. So, lambda 1 2 they are -1 and 2, and so the eigen values have different signs. So, this is not a node, this is not a node, okay, this one. Okay. But also you will see that you cannot decide whether this is an attractor or a repeller, okay, because with respect to x axis this is attractor, okay, and with respect to y this is repeller, and such type of mixed case they are known as saddle points. So, here the fixed point is known as a saddle point. Why saddle point? Now, you think that on a horse there is a part which is called a saddle, and that one point which is considered to be the minimum on the other direction which is perpendicular to that, this can be considered to be the maximum. Okay. So, you see that one point is the point of stable equilibrium in one direction, and the same point is the point of unstable equilibrium, okay, when it is considered along the direction which is perpendicular to that. Okay. And this type of situation is analogous to what we are now considering, and that is why we have given the name of saddle point. Okay. In the next lecture we will come back to very special type of system where you will have complex eigenvalues. Okay. And with that we also try to connect how the classical mechanical systems can be analyzed using this type of methodology. Thank you very much.